A classic problem in introductory physics, both algebra and calculus-based, is the motion of a mass through a straight tunnel, which connects two Earth locations, assuming that only gravity is acting on the mass. This problem was first discussed by Plutarch in the 2nd AD century, but could be solved precisely only after Newton proposed the universal law of gravitation in 1687. We can imagine the mass as a shuttle that moves passengers from one location of the Earth to another. For this reason, this problem is often referred to as the gravity train. Let's indicate by lowercase g the gravitational field and by uppercase G Newton's gravitational constant. Newton's universal law of gravity states that the strength of the gravitational field of a point mass m at distance r is given by Newton's gravitational constant times m over r squared. Using the field of a point particle, Newton derived his shell theorem. For a uniform spherical shell of mass m, the gravitational field vanishes inside the shell, but outside the shell, it is identical to that created by a point mass. Using the shell theorem, we can establish a more general theorem for any object with a spherically symmetric density. In such a case, the gravitational field for any distance r is identical to the field created by a point charge whose mass is the fraction of the spherical object's mass within a sphere of radius r. This result will be used for working out the motion of the gravity train. Given a tunnel of length 2 times x0 between two locations, A and B on Earth, consider the great circle that goes through these 2 points and has center at the center O of the Earth. When the two locations are antipodal, the tunnel goes through the center of the Earth. That is, it becomes a diameter, and x0 is equal to Earth's radius. I will introduce a coordinate system with origin at the center of the Earth, an x-axis parallel to the tunnel and a y-axis perpendicular to the tunnel. Let the shuttle be at a random point P of the tunnel where the distance from Earth's center is r. The only force on the shuttle is the gravitational force, that is, its weight W, which is equal to his shuttle's mass m times the gravitational field g at the point P. If big M of r is the mass of the Earth contained in the sphere of radius r, applying the theorem for the gravitational field due to a spherical distribution of mass, the weight of the shuttle is given by Newton's gravitational constant times the mass of the shuttle times the mass of the Earth contained in the sphere of radius r divided by r squared. The fraction of Earth's mass within a sphere of radius r can be computed from the density of the Earth rho and the volume of the sphere. The density of the Earth is the ratio of Earth's total mass by its total volume. Combining the two equations, we find the mass m of r of a sphere of radius r as a fraction of Earth's total mass. Substituting the previous result in the formula for the shuttle's weight, we find that the weight is proportional to the distance from the center of the Earth. The force that moves the shuttle through the tunnel is the horizontal component Wx of the weight. This component is the weight times the sine of the angle theta that the line OP makes with the y-axis. And the sine of theta can be computed easily as the abscissa of the point P over its distance from O. Notice that, due to its orientation, the algebraic value of Wx is opposite of the algebraic value of x. When everything is considered, we find that the shuttle is subjected to a restoring force which is directly proportional to the distance from the midpoint of the segment of B. This is exactly the condition for simple harmonic motion with constant k. Knowing k, the angular frequency of the oscillations is given by the square root of k over the shuttle's mass. And this can be converted to the period of oscillations by inverting the angular frequency and multiplying by 2 pi. This period is the same for all tunnels AB, independently of the locations of the points A and B. Substituting the values for Newton's constant, the radius of the Earth, and the mass of the Earth, we find that a gravity train will oscillate with a period of 5,127 seconds or 85 minutes. The trip between the two locations lasts half a period or about 42.5 minutes. Alexander Klotz has published in the American Journal of Physics an article with an improved calculation based on the internal layers of the Earth. His result for the trip is 38 minutes, not far away from the 42.5 minutes. The exact way the shuttle moves inside the tunnel is a sinusoidal oscillation, with amplitude the half-length of the tunnel x0. For a tunnel passing through the center of the Earth, x is just the radial distance from the center of the Earth and the amplitude equal to the Earth's radius. The shuttle, being a simple harmonic oscillator, has velocity which also changes as a simple harmonic oscillator with amplitude the angular frequency times the oscillation amplitude. At the middle of the trip, the shuttle has its highest speed. For a trip through the center, this is 7,841 meters per second or 28,228 kilometers per hour. This is a crazy fast speed. Finally, the acceleration of the shuttle is also a simple harmonic oscillator with amplitude the square of the angular frequency times the oscillation amplitude. For a tunnel through Earth's center, the amplitude is the value of the acceleration of gravity on the surface of the Earth, about 9.8 meters per square second. The previous form of the acceleration expresses the acceleration of the shuttle as a function of time. When this acceleration is expressed as a function of position, for a tunnel that goes through the Earth's center, the acceleration is exactly equal to the gravitational field at the position of the shuttle. And with this comment, I have concluded the video. I hope you liked this problem. If you did, please subscribe to my channel to help the creation of more content like this. Thanks a lot for your support.